Today we're going to be talking about limits of various functions. The first function we're going to start with is the reciprocal function. Reciprocal functions look like this. They normally involve fractions and they can have functions on the bottom and the top. Let's start with the parent function 1 over x. This function has an asymptote at x equals 0. An asymptote is when you have variables in the denominator of your fraction, and you set that equal to 0. So x equals 0 on the bottom is our asymptote, but say we had 1 over x plus 2. We would have to set the denominator x plus 2 equal to 0. Therefore, x equals negative 2 would be our asymptote. Whatever is on the bottom of your denominator, set it equal to 0 and solve for x, and that is how you find your asymptotes. Let's try to find the limit of this function. The limit of 1 over x as x approaches 5. Now, the first thing that we always try to do when we have to solve limits is just plug in the value directly. So we're going to plug in 5 in for our x over here, and we get 1 over 5. And that's the limit as x approaches 5. Pretty easy, right? Sometimes you end up getting 0 over 0, or infinity over 0, or some other indeterminate form, which I talk about in previous videos. In that case, we sometimes want to make a graph, or we want to make a table of values, or manipulate our equation in other ways in order to solve the limit. But in this case, it was pretty easy. We just plugged it in and we got an answer. Let's try finding the limit at 0. Now here we are going to run into a problem. So let's see. Limit as x approaches 0 of 1 over x. Well, we have an asymptote at x equals 0. And if we just plugged in 0, we'd get 1 over 0. That's one of our 7 indeterminate forms. X equals 0 is an asymptote, therefore our limit will not exist at that point. So what we just went through were two-sided limits, the limit as x approaches 5, the limit as x approaches 0. Now we're going to talk about one-sided limits. This is another way to tell if your limit does or does not exist. We can check the limit as x is approaching 0 from the right-hand side of the function, and we can check the limit as x approaches 0 from the left-hand side of the function. So I put a little positive and a little negative next to my 0. These are one-sided limits. If you find the limit as x is approaching 0 from the right, and then you do the same thing from the left, and the limits match up, that means that the two-sided limit as x approaches 0 is that value. If your one-sided limits do not match up, that means your limit does not exist. As x is approaching 0, coming in this direction, our y value, which is what we're looking for when we solve for the limit, we are looking for the y value as x is approaching a certain value. In this case, x is approaching 0, but specifically from the right-hand side, our y value is going to get bigger and bigger and bigger, so our y value keeps increasing forever, and it will never touch 0. So as it's getting closer and closer to 0, it'll just keep going closer and closer to infinity on the y-axis. So this is going to be positive infinity. When we are approaching 0 from the left-hand side, the graph will keep getting closer and closer to 0, but it will never touch. We'll keep going towards negative infinity. Now let's check if these one-sided limits are equal to each other. Well, one of them is infinity and the other one is negative infinity, meaning they are not the same, and that means our limit does not exist. Now we did verify this by just plugging x equals 0 into our function and looking at the graph. We could tell that we were never going to touch 0, therefore the limit didn't exist. But you can also verify it by using left and right one-sided limits to make sure that the numbers are not the same and that your limit really doesn't exist. Let's try a bit of a trickier example. The next question we're going to go through is the limit as x approaches 2 So this is also a reciprocal function because you have a fraction within a fraction. The first thing that I would try to do is just plug 2 in directly. But as we can see here, if we plugged in 2 down here, we would have 2 minus 2, which would give us a 0 on the bottom, and anything divided by 0 is indeterminate form. Let's try manipulating the equation, which is usually easier than having to plug in values, make a table of values, make a graph. We are just going to try manipulating it and see if we can cancel any terms out and then plug 2 in again. So I am going to simplify the top by making this 1 part of this fraction by multiplying the 1 by x minus 3 over x minus 3, then plus 1, and it would all go under one denominator, divided by x minus 2. X minus 3 plus 2 just gives you x minus 2 over x minus 3, and all of that is divided by x minus 2, which I'm now going to write out as multiplied by 1 over x minus 2. Now we can cancel these terms out, and we are left with 1 over x minus 3. Now if we try to find the limit as x approaches 2 of 1 over x minus 3, we have 1 over 2 minus 3, which is 1 over negative 1, which is negative 1. So our limit is negative 1. Now let's talk about exponential functions. An exponential function is anything that has a variable in the power, something such as e to the x, 5 to the x squared, 3 to the 2x, and so on. Now finding limits of exponential functions can be tricky, but there are certain limit rules that we can follow. I've put some exponential limit rules up in this corner here. Now let's try this example. The limit as x approaches infinity of 5 to the x. Well, usually we always try the direct plug-in method, 5 to the infinity. Well, if you look at these rules, this tells us that the limit as x approaches infinity of b, which is any number, in this case 5, to the x, equals infinity, if b is greater than 1. In our case, we have 5 to the x instead of b to the x, and b, which is 5, is greater than 1, meaning 5 to the infinity should just give us infinity as an answer. That is how you would apply one of these rules. Now let's try another one. The limit as x approaches infinity of 3/4 to the x. If we try to plug that in, 3/4 and plug in x as infinity, what does 3/4 to the infinity mean? You probably don't want to guess that the answer would just be infinity, so I would memorize these rules. If we look at rule number 3, it says the limit as x approaches infinity of b to the x, in our case b is 3/4, equals 0 if b is between 0 and 1. 3/4 is between 0 and 1, which means that our limit should just equal 0. That's how you apply these limit rules. Let's go through an example where we need to use something called L'Hopital's rule. So this rule implies that when you have a limit that gives you 0 over 0 or infinity over infinity in determinate forms, when you use the plug-in method, you are able to take the derivative of the top and the bottom of your function and then try the limit plug-in method one more time. Let's try the limit as x approaches 0 on 3 to the 2x minus 2 to the x over 2x. Our first train of thought is always to just plug in the value that we're given for x. So 3 to the 2 times 0, 1 over 0, which gives you 0 over 0. that is one of our indeterminate forms, in which case we can use L'Hopital's rule. Usually it's used when you have just infinity over infinity or 0 over 0, when you try to plug in your x value and you end up getting one of these forms. That's when we can use it. So now that we've confirmed that we do indeed obtain an indeterminate form when we plug in x equals 0, we are going to take the derivative of the top and the bottom of our function. In this case, we only take the derivative of the top and we take the derivative of the bottom separate from one another. So the derivative of the top should give you 2 ln of 3. Now we can try to take the limit of the top and the bottom one more time by plugging in 0. 2 times ln of 3 all over 2. 2 to the 0 should give you 1. As you recall, anything to the 0 gives you 1. 3 to the 2 times 0 is 3 to the 0, which is also 1. So we have 2 ln of 3 minus ln of 2 over 2. Putting that in your calculator should give, and that is our limit. Let's move on to our next function, which is going to be logarithmic functions. Log of x looks something like this, and ln of x, which is a natural log of x, looks something like this. Ln x, log x. So let's go through a quick limit using ln or log. Let's try the limit as x approaches 2 of ln 2 plus x. So the first thing we want to do is just plug in 2 anywhere there's an x. So ln of 2 plus 2 equals ln of 4. That was pretty easy, right? This is actually 1.3862. Let's try a second example using logarithmic functions and L'Hopital's rule. The first thing we're going to do is just try plugging in the numbers directly. Log of 10 with a base of 10 means 10 to the power of what will give you 10. The answer to this expression is 1, and that gives us 1 minus 1 on the top and 10 minus 10 on the bottom, which gives us 0 over 0. This is indeterminate, so now we will try using L'Hopital's rule and differentiating the top and the bottom independent of one another. 1 over x ln 10 divided by 1. Now we will try plugging in 10 one more time. 1 over 10 ln of 10 divided by 1, which is just 1 over 10 ln of 10. And that is our answer to the limit as x approaches 10 for this function. Next, let's continue on to finding limits for our last function, trig. The trig functions that we're going to talk about are now, unlike any of our other function families, trig functions have a ton of identities that you can use to manipulate your equation. If we try to sub pi over 4 into our equation, we will end up getting 1 minus 1 over approximately 0.7 minus 0.7, which will give us 0 over 0. So we can either use L'Hopital's rule to try to differentiate the top and the bottom. There are usually trig identities that we can use to manipulate our equations. So I'm going to do those first. One common trig identity is that tan of x is equal to the sine of x over cos of x. We are going to use this simple identity. Instead of tan of x, we have sine of x over cos of x. And I'm going to leave the bottom as it is. Next, I'm going to make one common numerator on the top. 1 just becomes cos of x over cos of x minus sine of x over cos of x. The cos of x can be one common denominator divided by sine of x minus cos of x. I'm going to bring the second denominator up into the first one, so we have it multiplied by a sine of x minus cos of x instead of having a fraction within a fraction. The next thing I'm going to do, and I can actually do it right here, is I'm going to factor out a negative and switch all the signs. And what this does is makes it negative sine of x plus cos of x, which, when you flip it around, is cos x minus sine x, which is the same as the top, cos x minus sine x. So I'm going to cancel these brackets, and we are left with 1 over negative cos x. Now let's try finding the limit as x approaches pi over 4. 1 over negative cos pi over 4 gives you 1 over negative approximately 0.7. And that is our answer. Next, let's talk about one more way of solving trig limits. This is called the squeeze theorem. So now let's talk about the squeeze theorem. We're going to use this to evaluate trig limits. However, it doesn't only have to be used with sine, cos, or tan. Let's talk about what the squeeze theorem is first. So in this case, g of x is the function we're finding the limit for, and f of x and h of x are sandwiching g of x in between them. But if f of x and h of x have the same limit at a, then g of x will also have the same limit because it is sandwiched between them. Let's do an example to see how this works before we move on to trig limits. Let's begin by trying to find the limit as x approaches 0 of f of x. And let's also say that the question tells us that f of x is sandwiched between g of x and h of x, like so. G of x is going to be 5 minus x, and f of x is going to be 5 plus x. Now, we can take the limit of each part of this inequality as x approaches 0. And now we can just plug in 0 everywhere there's an x in this and this part of the equation. So what we end up getting, the limit as x approaches 0 of 5 minus x just gives you 5. Now the limit as x approaches 0 of f of x, which is what we were originally trying to find, we still don't know. But the right-hand side of the inequality, the limit as x approaches 0 of 5 plus x, is also 5. Now, what the squeeze theorem tells us is that if f of x is sandwiched between two functions, g of x and h of x, which it is, and the limit for g of x as x approaches 0 and h of x as x approaches 0 is 5. Therefore, the squeeze theorem tells us that because the limit of the functions on both sides as x approaches 0 is 5, the limit of f of x as x approaches 0 must also be 5. So that's how we use the squeeze theorem. Now let's do an example using a trig function. Let's find the limit as x. Now if we try to graph cos of x, it will look something like this. It goes up to +1 and down to -1. So we can say that cos of x is sandwiched between -1 and 1, which is also the same for sine of x. However, the function that we want to find the limit for is x squared cos of x. So what we're going to do is multiply each side of the inequality by an x squared. So now we have negative x squared cos of x. We always want to get the function we are trying to find the limit for in the center by multiplying the entire inequality through by anything else that we have attached to our cos x or sine x. Sine x. Just going to change colors here. So now we know that x squared cos of x is sandwiched between negative x squared and positive x squared. Let's try to find the limit as x approaches 0 for each part of the inequality. Now the limit as x approaches 0 for negative x squared is just 0 when you plug it in. And the limit as x approaches 0 for positive x squared is just 0 when you plug in x into x squared. And what we're left with in the middle is what we were looking for, the limit as x approaches 0 of x squared cos of x. Now because the limits of the functions on the left and right hand side as x approach 0 are 0, therefore the limit of our function is also going to be 0, according to the squeeze theorem. So that's how you use the squeeze theorem to evaluate functions, and we just did an example using a trig function and a regular linear function. Now let's talk about some limit rules, including addition, subtraction, multiplication, and division, before we finish up. So before we go, I just wanted to discuss some limit rules: addition, subtraction, multiplication, and division. Let's just do a quick example to see how these rules work. Let's take the limit as x approaches 2 of x squared plus 3 over x plus 1. Now you might think this looks like a reciprocal function, and it is. However, there is an easier way to solve this. Rather than trying to simplify the fraction, simply take the limit as x approaches 2 of the numerator and take the limit as x approaches 2 of the denominator, and plug in 2 everywhere there's an x, so 2 squared plus 3 over 2 plus 1, which gives you 7 over 3. Let's try one more example up here. The limit as x approaches 2 of x squared plus 3 times 3x. Now, rather than having to expand this entire equation, all we have to do is take the limit as x approaches 2 of x squared plus 3 and multiply it by the limit as x approaches 2 of 3x. So let's sub in 2 everywhere there's an x, which gives us 42 as our answer. And that's how you apply limit rules. I'm going to leave a link in the description below to my blog post if you'd like more information on how to solve limits for various functions. Bye for now.